So, okay. I think everybody's back now, right? Well, for the most part. Oh, a few more people come in. Right. So I have 2 lectures back to back now, and they'll be my final lectures. And I'm going to finish my crash course on wave propagation in high contrast media. So if we just remind ourselves what we did in the last few lectures, we were studying this generalized wave equation in a periodic structure, and we wanted to understand for what frequencies omega do you have time harmonic waves to this time harmonic solutions to this equation. And if you remember, if our periodic media was actually just homogeneous, so constant coefficients, then we showed that waves will propagate for all frequencies in all directions. And then in the last lecture we started studying periodic coefficients and realizing that the mathematical problem to study is the block problem and block waves. And what we showed was that actually there are forbidden regions of frequency where waves cannot propagate in any direction. And there was many other interesting wave phenomena of periodic media that I didn't quite go into but alluded to, about you can have a possibility of waves only propagating for certain polarizations and maybe even only for certain wave number. But then we concluded the lecture with showing if we had some composite structure with a small microstructure, so its period is very small with respect to the observable length scale. In the language of Curio, just spent the last 20 or 30 minutes discussing this, so it should all be fresh in your minds. What we showed there was for a fixed frequency and a small enough structure, then our waves behave like long waves, and the so-called long wavelength approximation holds, which says actually, well, you will have waves propagating for all frequencies in all directions because the composite media will effectively behave like a homogeneous media. And precisely the material coefficients of the homogeneous media were the Hessian of the eigenvalue, the first eigenvalue of the block problem at the origin. Or rather, if it's a system, this eigenvalue has a multiplicity, say d, and then there will be d eigenvalues that intersect the origin, and you will have to consider the Hessian of all these bonds. So what I want to discuss today is, one conclusion of yesterday's result is for fixed low frequency, then for a normal periodic media composite, you shouldn't expect that waves cannot be localized and they will propagate through this media. But from the point of view of applications, it might be interesting to ask ourselves, how can we create a composite media with a given microstructure such that low frequency waves cannot propagate through this media? And the one answer to this question is so-called high contrast. So let us now begin with the study of high contrast. So first, the motivation. If you remember, I had this picture that we have a wave somehow propagating through the material, and the long wavelength approximation tells us that the periodic structure is small compared to the wave, the length of the wave. So the wave will see effectively a homogeneous material. So, and if we remember from our last few lectures, we will say that block waves, well, they are actually plane waves, right? So block or plane, because I'm going to consider it will propagate in omega 1, say, with the wavelength. If you remember, it will be lambda, and it will be given by 2 pi over k. And we showed for a homogeneous material, k is just proportional to omega, and the constant of proportionality is given by the coefficients of the material. So, sorry. Well, let us just, for the sake of discussion, we're studying now this equation, the acoustic equation. Oh, interesting. Did I do it? Oh no, not good. Maybe. So if you remember, so for this equation, in a homogeneous material, plane waves propagated, and precisely they propagated with respect to the following dispersion relation. So what we see here is we have square root of A1 2 pi over omega, where A equals A1 in Q1, paying attention to this picture, and say, be consistent with the notation I was using before, A2 in Q2. Okay? And, well, but the plane waves will propagate in the second material. They will be given with 2 pi over k, which equals square root of A0 over omega. Right? And this was the basis of our intuition as to why the material should be effectively homogeneous for a fixed omega, because the wavelength is very long with respect to the structure. I just remember now. So, but now let us suppose that A2 is not, A2 scales with our, so we were considering a problem with period epsilon. And let us suppose that A2 scales with epsilon in the following fashion. Just, where let's just say epsilon squared. Then the wavelength here is now equals to 2 pi over omega epsilon, right? So it's an order epsilon. So now we no longer have this long wavelength approximation, because inside the material, inside the inclusions, the wavelength of the wave will be of the same size as the inclusion. And this, it will happen for all frequencies and for all periods, no matter how small the structure is. And this, so it's the period of the microstructure. So, and this special scaling is the so-called critical scaling, or double porosity scaling in problems in mathematical literature, and it gives rise to the intuitive notion that you can't expect the long wavelength approximation anymore. And in fact, there is some kind of scale interaction effect where you see that inside the material 1, the wave wants to be long, but inside material 2, the wave wants to be short. And this, we will see now that this is a very good candidate for creating microstructure material that have band gap structure, and waves will not be able to propagate through this material at certain frequencies. And the reason for this is because it will always feel the microstructure. And if you for this one in the context of acoustics, so I showed in lecture 1, the velocity of the gas particle is, for the acoustic approximation, is given like this. So phi is the potential of velocity. Okay, yeah, so I suppose, unfortunately, you weren't here from my previous lectures, so I gave quite a bit of notation. But in fact, we were studying plane waves of the form kx minus omega t. So k is, yes, the wave number, and omega is the frequency. And the absolute value k is just the magnitude of the wave number, wave vector, which I call the wave number. This little a is the wave speed. This little a is the speed of the wave, or well, the square of the speed of the wave. And in the acoustic approximation, a squared is precisely acoustic approximation. Adiabatic material, the pressure is a function of density only, and a squared is the gradient of the density at the initial state, and it gives the speed of the wave. Yes, yes, so now we have some periodic material, and we say, well, the inclusion material, the wave speed is actually the same order as the inclusion. So now the wave will always propagate with finite wavelength through this material, no matter how small the inclusion is. So you can no longer have this long wavelength approximation. So, and now we want to study the wave properties of such high contrast material. So we will let, so now, okay, we can keep this first picture, keep this. And there are several ways to study this problem. I could continue to discuss it in the way I discussed it with the classical one by studying the block problem, but what I would like to do is actually now use two-scale or multi-scale asymptotics to study this problem, because I think it gives some extra insight as to what's going on. And the density, we will never assume that the density is doing anything strange. The density is just always finite, always avoid the one. So we're going to study this problem, star here, equation 1, using multi-scale asymptotic expansions. So we're going to assume that our field, which is now depends on epsilon, has the following form. We should have to go one more. Let me just write this. So what the idea of these asymptotic expansions is we want to find, this will be the leading order behavior of the wave, and we want to find what kind of equations this function satisfies. And the way we do this is by substituting this equation, this ansatz, into this equation, and then gathering the terms with equal powers of epsilon and equating coefficients. So just for the people who have not seen this before, I'll just do maybe one of the substitutions. So if you remember, this one was symbolically, it actually meant the following problem. You can either understand it, for those of you who understand weak formulations, you can understand it in the weak sense, but if not, you can remember that I said in the second lecture that this is of the following form. Oh, and now put epsilon. You see, this is always why you have so much fun with systems. You have to plan ahead where you're going to put your symbols. So now this is J. So throughout all of this, just imagine that X and T are fixed, and we are just discussing, and because what's important is the Y variable. What am I talking about? Okay, and we had the similar equation. And there was a similar equation inside the inclusion, right? And I'll be lazy and just replace this by R, and I'll put omega R here, where R is 1 or 2. And these two equations were accompanied with boundary conditions, precisely that the function is continuous across the interface, and the flux is continuous. If you write it in vector form. But this is the problem we are studying, the wave equation in each material, and then there are these infinitely many interface conditions, and what you need to do is substitute this ansatz into all of these equations and start gathering terms. And I won't do it fully because I don't have as much time now, but let's just to remind you all. So imagine if I wanted to take the jth derivative of a function. Well, what you're going to end up with is precisely d by dxj plus epsilon minus 1 d by dyj, right? Of u, x, y, t, y equals x over epsilon. Okay? So then what you can see is, for example, if I plugged this ansatz into the first equation, then I would have equations of the form. So I would get. So should I do this or shall I just? Okay, so we can plug the equation into. Let's substitute this equation 2 into 1. Safer. And for example, we would have rho 1 ij du0 j squared dt y and then you get an epsilon minus 2 and then you would have an equation of order epsilon minus 1, and which I will gather together like this. And one more term for the epsilon minus 1. d by dxj this time of the tensor du0 by dy. No, yeah, it's yeah. There's no interaction with the no scaling with time and the macrostructure. All I want to focus on is these special effects for now, and then we can do the same at epsilon 0, right? Well, I've started now. I might as well finish, but I won't do it for the rest of the equations. I'll just give you the answer, and it can be an exercise for yourselves to justify. So x here, xl, and then now what do I want? I have a 1 here, so I need to put a y here. And I have a 0 here, so I can put an x. Right? And then plus order epsilon, for example. And then what you need to do is you need to start equating coefficients. Because if the left-hand side equals the right-hand side, then, for example, this term needs to be 0. And this term needs to be 0 in the front of epsilon minus 1. And then this term in front of epsilon to the power 0 will equal the right-hand side. And I want to keep this, so I will rub this out. So, and you do this. I just did this for material 1. Actually, for material 2, it's a lot easier because you have epsilon squared in front of your coefficient, so you only you have no terms of order epsilon minus 2 nor order epsilon minus 1. The only other thing you have to do for yourselves, with a little bit of exercise and dexterity, is just plug it into these interface conditions. But let's gather the equations and see what we get. And it's important that I spend a little bit of time doing this, because I'm precisely going to spend the rest of my time here discussing the structure of these equations that we arrive at. So what do we get? We get, for the first equation, when you've done everything I just said, for an exercise, so you can have this as an exercise to show that we have, first of all, so for fixed, and this comes with the following interface condition. So if you look at the picture for what I mean by Q1 and what I mean by gamma and N, so this is our first equation. Let me write all of the equations. This is our good. Okay, we're gonna have to split this board into 3 now. So our second equation, if you once you've plugged everything in, right? But again, this is just an equation on the region where the coefficients are order 1, not small. So this is terminology we usually call this the stiff phase, and this the soft phase for mechanical reasons if you're in elasticity. And again, we have some interface conditions, which I will group together in the following form. Of course, these equations look kind of simple due to the mathematical notation, but once you start considering particular examples, these can be quite notoriously difficult. But for the purpose of analysis, it's fine. We can still do analysis with these things. So this is the second equation. And then we have a third equation. Again, I must write it, it's important. Give me a few minutes. Now I'll just group everything together in one go, as you've started to see. Hopefully there's a particular structure. Again, this is a function of y here, and I should keep my variables right. X, y, t. Okay, and what is this equal to? Rho 1 ijk d squared u0 dt squared for x, y, and t. And now y is in Q1. But now, because of this epsilon squared term here, we have some non-trivial contribution from of the function inside this region too. So we have another equation. Okay, so we have one equation in Q1, another equation in the surface Q0, and when we put into the interface conditions, we would have had the following condition on the boundary between the two regions. Oh, yeah, no, that was fine. Sorry. Okay, YL, X, Y, T, N, I, Y, on this boundary. Okay, so it might look a bit complicated at the moment, but remember what the goal was. We wanted to believe that up to leading order, our solution was of the following form. I rubbed out. I'll just write it here for a reminder. Right? We had, I wrote more explicitly what these terms were, but up to leading order, we want to guess that our solution looks like this. So we need to arrive at some equations for this. So, and to do this, we need to now study these three equations. And the reason I wrote them explicitly and not just the answer, it will become more apparent as we go on. But let's look at the first equation. So again, you can, maybe can this be some homework? Show that U0 solves A, applies this, right? This. Oh, that's C1 IJKL EU0K DYL. Okay, so the way to do this, the hint is that you multiply this function by U0 and integrate over the region and use integration by parts. And what you will show is this condition. Now, remember that our coefficients, so I should have said here, so I want to satisfy this condition. And to satisfy this condition, we would just make sure that U1 and U2 solve this condition. I will just actually, I'm going to assume this one. Symmetric matrices M. And I will assume the same. And I will assume the same for the second one. So from this equation and from this condition, then what you will see is that U0 has a very special structure with respect to Y. So this condition plus the ellipticity tells me that the gradient of U0 is 0 inside the stiff phase Q1. So the function is constant inside the stiff phase because it's connected set. So actually you can just assume that the function is constant everywhere plus some arbitrary function inside the inclusion. And if you notice, this function inside the inclusion still depends on the variable y, which was our microscopic variable. So this variable tells you where you are with respect to the periodic reference cell. So where you are with respect to the microstructure. So in the homogeneous case, when the equations were just order 1 and there wasn't this special scaling where you had a long wavelength approximation, then we showed that up to leading order, our solution is just constant. with respect to y. But now we have this non-trivial behavior, and precisely the non-trivial behavior is inside these inclusions, where the wave speed has been chosen such that the wavelength is order 1. And it's precisely this sort of effect that is going to keep track of the microscopic behavior of the solutions to these equations. But we still haven't found u0 now, because our function u is arbitrary and our function v is arbitrary. So we have to carry on a little bit more to determine what kind of equations these functions solve. So now we have an important aside. We want to study equations of this form, b and c. And if you realize that if you look at these equations, they are of the form divergence of c1 grad say w equals f. They are of this form, but we have just shown that the space V, say now you can ignore this Sobolev space if you don't know what it means, but say just imagine smooth periodic functions. We have shown that the space of smooth periodic functions here is not 0, right? In fact, this space in this particular example are characterized by the functions of this form. They are functions constant in the matrix and arbitrary inside the inclusion, where Q1 is the matrix and Q2 is the inclusion. So, because this space is non-zero, this is the kernel of the operator associated to this problem. So, if you have solutions to such a problem, the right-hand side must be orthogonal to functions inside this space. And in fact, you can prove that this is a necessary and sufficient condition. So, what does it mean? Look at equation B. So our first order corrector u1 will only exist if and only if the right hand side is 0 on functions inside this space V. But if I rewrite equation B first, no, I don't need to rewrite it actually. Let's just look at it here. This term, we just showed that u0 satisfies this condition, right? So this term is automatically 0. Yeah? So we only need to study. So I'll just keep it crossed out for now. So we only need to study this line equals 0 and this line equals 0. And now if I multiply this equation by an element from this space and use integration by parts, you will see that the right hand side is automatically 0. So what I mean is just if I take d by dyj, okay, so this can be an exercise again. I take the left hand side, which is our f, just for you guys that don't do Sobolev spaces, let me put here. So this is an infinitely smooth function, and this hash means it's periodic with respect to Q. So you can show that this condition holds. So what does it mean? It means that this function u1 always exists. So u1 exists, but it still doesn't tell us anything about u0 because the right hand side automatically holds for u0. So now we go to equation C. And again, let's carefully look at this. We want to ask when does the function u2 exist. And you realize that u2, again, solves an equation of this type for our right-hand side f. But now the right-hand side f is quite complicated, and it doesn't automatically solve this so-called solvability condition. And you actually have to impose this solvability condition. And if I write the solvability condition here, what does it mean? It means that for u2, so there exists u2 if and only if. So I will write it like this: integral over q I write it like this, rho, okay? So using this notation now, so I'm integrating over the whole cell, plus you have the, again, this can be an exercise. It's just basically integration by parts. If you know how to integrate by parts, you just keep doing it until you get sick of doing it, and then you will end up with this equation. Okay. Actually, if you remember, this function is this equation is supported on Q1, and on Q1 U0 just looks like a function of x. Dy here, and there is another term, right? Now, on the inclusion, U0 looks like U plus V, but we differentiate with respect to Y. And then V D phi I Y Yj. So this is our solvability condition, right? Doesn't looks maybe a little bit abstract and not very useful at the moment, you might say. But now let's remember that our space V has a very special structure. It is precisely functions that are constant with respect to Y, and then functions that are supported on the inclusion with respect to Y. So if I just let phi I be some constant, okay, in this equation, what do I want to call this equation? We can call it D now. So all you do is just choose phi to be constant, right? So we look here, this tells us that, I will write it this way. Oh. Yes. Oh. Yeah, let's write it this way. Oh, sorry, let me put dy here. X and t, right? And now we look at the right hand side. Well, this is differentiation with respect to y, so this term disappears, and we are only left with this term. But this function is constant with respect to y. So you can pull this function out, and I will keep it in the following form for the moment. Right? Because of the arbitrary choice of the constant, and this is in ID. Okay? And then similarly, if you chose phi to be an arbitrary function supported on the inclusion, well, this function has integrating over the matrix Q1 only, so this term is 0. So you just end up with this equation equals this on the inclusion, and this has the following strong form. I did an integration here, so there's a minus. So this has the following form. Rho 2 ij d squared by dc squared plus u by t. This is a function of x equals divergence with respect to y of the function in the inclusion. This y in the inclusion. So it's so let's just have a look. So, well, before I rewrite it in a nicer form, if I look at this equation, there's one little observation that you need to make as well. Is if I look at this equation b, then this is a partial differential equation with derivatives with respect to y of a function. This now is supported on the inclusion, so this can be written by u of x, if you because u0 is independent of y in the inclusion. Okay, and then because this function is linear in x, for each parameter x, it's just a linear PDE in y. You can see that the fact that u1 has a special structure. It's not quite important, but I'll just write it now. So you can guess the structure for u1 if you like, or you can justify it. And then when you put this inside here, you will see, and I will stop writing index notation now, it's a concept time. You will see that the function n must satisfy the following problem. Gradient with I got a little bit compactor. So you have divergence with respect to y of this function of y, tensor, of the gradient with respect to y of MP, plus the tensor product of these two vectors. So this again is the weak formulation for this problem B. Once I've substituted this ansatz into this equation. And what it means, if you look carefully at this first of the two equations, is you can write u1 in terms of n and u, and you can then take, because this u is independent of y, it can take it out of the integral. And finally, after a little bit of work, and hopefully you followed enough of it to believe it, what you end up with is you see that u0 xy of t plus u of x plus v of xy and t plus order epsilon solves the following equation. So divergence with respect to x of some constant where this bracket, I've taken it to mean integral with respect to y. So if the input is a function of x and y, then this is a function of x only. Oh, I shouldn't have written that there. I'll rub it out. But that means integral with respect to y. So we have an equation, and this equation is purely on the spatial variable x. But then because we chose this special scaling for the wave speed, we have an equation on the variable y, the microvariable, and this is only on the inclusion. And that equation is of the same type. It is the divergence now with respect to y. It looks better in compact form, right? write x, y, t on this side too. So we take a few minutes to just absorb what's happened. So now we have chosen a periodic material whose inclusions, the wave speed is such that the wave is always of the same size as the inclusion. The wavelength is always of the same size as the inclusion, no matter how small the inclusion is. So even if the inclusion is very small, and we have some looks almost homogeneous to the human eye, actually the solution to the wave equation solves the following system of two coupled equations. Right? This is an equation on the spatial variable x only, and this is an equation on x and y. And these equations have a very important structure that here with this presence of the v. So the homogeneous equations, if you remember, when we never chose this special scaling, this equation was identically 0, and you just had a homogeneous wave equation. But now we have these two non-trivial contributions. And I feel, how much time do I have? I feel I spent too much time on this. Oh, it's already. So, okay. For 10 minutes now, let's just understand what the effects of these equations are. In the simple case, I write the vector case because the unusual effects that we're going to motivate and hope for, I need the vector structure. But let's just look at the simple case. So imagine now that we chose that that it wasn't a system, it was a scalar equation. So we were just looking, actually, and we just set the density to be 0. And we were just looking at this equation. Then we would. Then this is just a scalar. U is a scalar and V is a scalar. And let's look at the. And so now U epsilon looks like U of x. U epsilon x y t looks like U of x plus V of x over epsilon t. Of the leading order, right? And U and V solve these two equations. Now let's assume that, well, U of x solves an equation that only depends on x, so we can now start thinking about our plane wave ansatz again. So is our wave solution approximately a wave? Right? For some constant a, for some scalar a. Our V is just some function v0. Okay? So let's look at this equation. What should we call this? So equation 4 here and 5, right? So 5 then takes a particular structure. It precisely looks like the divergence of y of C2, which is a scalar in this case. And now density is 0. So this is our equation for y, for v, and you see, again, this is now, this is a, I should have not gone 2 steps at once. Let's do it in 2 steps. And again, and now you can guess the particular structure of this function v. Because again, this is a differential equation in y only, and this right hand side is a function of x only, but this is a function of x and y. Just to get to the point, if we take this particular guess, then we have that the divergence y of b of C2 grad b minus omega squared b equals 1. Okay, and b equals 0 on the boundary. And if you substitute, and then if equation 4 then takes the form divergence x equals what do we have here? We have omega squared plus omega 4 absolute value b u. And you can call this a beta of omega squared if you like. First introduced by Zhukov. So you have this very particular structure. And what you can see here is you've decoupled these equations and we're just left with this equation. And if you like, this is our how the waves behave in the high contrast media. And you had now, and this looks a lot like what we saw for the homogeneous equations, right? But on the right hand side we had something independent of the frequency. But now we have something that depends on the frequency. And I won't go into the details just to conserve a bit of time, but you can do a spectral decomposition on this problem, right? The operator associated to this has countably many eigenvalues and eigenfunctions, so you can do Fourier analysis and Fourier decompose this function in terms of the eigenvalues and eigenfunctions. And then what you can see is this beta of omega as a structure given by this picture. If I put lambda here, it has some kind of and where these asymptotes are the eigenvalues, certain eigenvalues of this divergence equation on the inclusion with the Dirichlet boundary condition. So now we want to, so now our right hand side, so well, now we want to study plane waves, right? So just right at the bottom, we do what we did in the first lecture, and we say, well, this looks like a homogeneous equation. So we can study some kind of plane waves, and it leads to the following problem. Just like we had in the first lecture, C of k of A equals beta of omega squared A. Why this way? And then we can do the type of analysis that we did in lecture 1. Remember, in lecture 1, the right hand side was independent of omega. So we said for each frequency, the right hand side was just equal to omega squared, sorry. So we said for each frequency omega, omega squared is nothing more than an eigenvalue of this positive matrix. And again, it's a positive matrix here, just as the same type as before. But now this beta of omega is actually a function in this scalar example, and you can see that for certain values of omega, the right hand side becomes negative, but the left hand side is always positive. So this is precisely, if you choose a frequency omega that lives in this region, in one of these regions, then you have arrived at your desired effect. But for these frequencies omega, there are no wave numbers k, such that there are solutions to this problem. So you have frequency band gaps. And actually, if I did the scalar, if I did all of this now, not for the scalar, but for the system, what we would have here is our usual tensor, our usual matrix on the right hand side that comes from the tensor. So just to remind you, if you've forgotten the first lecture, this was, just to remind you, Cik equalsCijkl KL Aj, like this. And if I did the systems now, not the scalar equation, and I went through this quite quickly, but if you carefully went through all of the steps in the same fashion, you would realize that this right hand side is not a function, but it's actually a matrix. And let's just imagine we're in 3 dimensions, so it's a 3 by 3 matrix, a symmetric matrix in fact. And in general, it will have 3 eigenvalues. And these eigenvalues can all depend on omega in the same fashion. So you can have, say, for a particular omega, maybe only 2 of the eigenvalues are positive and 1 of the eigenvalues are negative. And then a small bit of analysis will show that for this frequency, you still have waves propagating in all directions again, just like in lecture 1, because this is a 2 homogeneous function of k, but you will have a reduced number of eigenfunctions, eigenvectors to this problem where the frequency is allowed to propagate. So this is some kind of, it means that although for this frequency inside the band, you have waves propagating in all directions, but you have a reduced number of polarizations. There are less choices of A that you can pick. And this is like a very crash course in why people study high contrast problems. So just to summarize, what you arrive at with this high contrast scaling is you end up with an equation, which I rubbed out, with the wave equation. And this wave equation was coupled in a very special fashion with respect to time. And in fact, this was what we would call a temporal non-locality, because of the presence of this beta function. And due to this temporal non-locality, you can end up with gaps in your frequency gaps for waves trying to propagate through this material. So that means, if you remember the picture in the very first lecture, it means waves of certain frequencies are not allowed to propagate through this periodic structure. And this can happen for any arbitrarily small frequency omega. Whatever omega you pick, you just pick your material such that this region lies, such that omega lies within this region. And I think that's a good point to have a 10-minute rest. And then what we will do when we come back is try and understand. I'll give you an hour crash course in the most recent advances in trying to understand how we can create not only temporal non-localities, which means that waves of certain frequencies aren't allowed to propagate, but how to create spatial non-localities. So waves in certain directions, k, will not be allowed to propagate for given frequencies. And this gives you the idea of this picture I showed in the first lecture of the human inside the bubble surrounded by a periodic material, and the waves will be guided around the bubble because they will only be allowed to propagate in some directions and not others. Thank you. So I'll see you in 10 minutes. Oh, and if you have any questions on the first part in the 10 minutes, come find me. So maybe I will finish in half an hour so we can finish at 1 o'clock. So that way it doesn't interrupt too much with the afternoon's activities. But, well, I very quickly, and you all had to work very hard to keep up, wrote these equations down, and everything I'm going to discuss now is just going to directly come from these equations, so we can take our time and just discuss some ideas a little bit. So let's just remind ourselves what I tried to show. It's good to recap because I appreciate I went a little bit fast and it's hard to keep track of everything. But basically the idea was, if our material coefficients have such a special scaling inside the inclusion, then the wavelength of the wave trying to propagate through this material is always of the same order of the inclusion when you're inside the inclusion. But when you're outside the inclusion, it is of an order much larger than your microstructure. And this intuitive idea manifests itself in the form of, oh, I didn't even finish, of two equations. The following equation here, which is purely a macroscopic equation for a function u and mean value of v. So if we remember, u will give us our overall behavior. So there's a nice little picture, I suppose, you can have. Where can I put it? I should just finish the. For some reason, I didn't finish the equation. Let me finish it. Right, and remember that v of x, y, t was 0 on the boundary. So, and a little picture I like to keep in my mind that you can have, if you want to plot your function u0, then somehow, with respect to the microstructure, it is of order 1, but with respect to the inclusions, it has some kind of oscillation given by the v. And this macroscopic equation, which is kind of what we would like to call our homogenized equation, has some integration over the entire periodic cell of v. So this is some mean value of the oscillation. But the equations themselves have some very non-trivial evolution inside the microstructure, which we remember even through the process of homogenization. So we've replaced this complicated equation here that has infinitely many interface conditions on gamma, and it has coefficients that are rapidly oscillating with respect to epsilon by this other system of equations where the coefficients are constant here, and we have equations with respect to x and y separately. And then we showed very quickly, you'll have to take if you would like, actually, I went for it too fast to give any nice feeling for this. But everything I discussed was first understood and exposed very beautifully by the late Vasily Zhikov in two articles in 2000 and 2004. And it's precisely on the spectrum of divergence type operators with high contrast coefficients. And basically what was said here is it showed all of the things, like if you look at the time harmonic waves, then these equations decouple, and you have this beta function, which is a function of omega, and you have these spectral gaps. Now, what this means here is some kind of temporal non-locality. This is what I argued. So now we want to keep on making our microstructure more and more complicated and try and understand, can we create some kind of spatial non-locality? So waves not propagate, so waves that are not only forbidden to propagate for certain frequencies of time, but for certain wave numbers of x. And there is the following idea. Don't know I can't remember the name of the paper, but one of the authors is in the audience, so maybe he can tell us the name of the paper. And I believe 2006. So Curio is one of the authors. Do you remember the paper? So in 2006 there was the following idea. Well, these equations create a temporal non-locality, but t can easily be replaced by a spatial variable. So for example, imagine now we have some structure and we decided that this was our periodic structure, but we decided t was now going to be a variable in the x3 direction. Okay? So then, and in this example, they basically were studying these problems for scalar equations, where your coefficient c now would be of the form c1, would be of the form epsilon squared 1, some diagonal matrix. Does everybody understand? I just reminded them about the beta function before you came in. Oh, well, yeah, I didn't quite have time to discuss this, right? But you have to you have to take the solution to the time harmonic problem and then take a Laplace transform. And then when you take a Laplace transform, does everybody remember what a Laplace transform is? So when you take the Laplace transform, you then end up with the eigenvalue problem, where omega squared now is your Laplace coefficient. And then you will have a nonlinear, an eigenvalue problem that's nonlinear in the, what is this? What is it called, this Laplace coefficient? Okay, I'll call it a Laplace coefficient. Then you have a nonlinear eigenvalue problem given by this beta function, where omega squared is now your Laplace coefficient. So if you then solve this problem, at least formally, and did an inverse Laplace transform, you would have a non-locality in this variable. And this will correspond to a temporal non-locality. Right? So now let's replace t with x3. Yeah. Okay. Maybe we can discuss it, because you already ate 20 minutes of my time this morning. And we're running out of time. So, and I don't want to eat Lewis's time, or Ricardo's, whoever's next. So formally, let's just replace t with x3 and do all of the same things I did very quickly in the last hour. Then you just replace t here with x3, t here with x3, and then all of this discussion I just said about Laplace transform, you just repeat it in your head, and I just replace Laplace transform with Fourier transform. So what does it mean now? My omega is no longer frequency now. It's actually just my wave number with respect to x3. So very formally, you have now created spatial non-locality in the direction of the fiber, not the temporal non-locality. So then there was the idea, which I will discuss now at some length before I run out of time, of Valery Smyshev in 2009. This is when I just appeared on the scene as his master's student, and his idea was, well, okay, so we can create temporal non-locality, and we can create spatial non-locality by just playing with the equations and realizing they're the same structure. But maybe we can combine the two. So I create spatial and temporal non-locality. And how do I do this? Well, I can actually just not replace t with x3, but imagine that I just had a periodic structure. So we still keep the time variable and we still keep the x variable, but I have a periodic structure of this form. And maybe I have coefficients that precisely, so in the high contrast case we had coefficients that were order 1 here and order epsilon squared here. And this very, say, artificial example in the scalar case will tell you that maybe in the inclusions you can have some variables, some derivatives that have this special scaling epsilon squared, and some variables that don't have the special scaling. So, but the reason I've gone through the efforts of writing all the systems in the first place is because it's more natural to think of this in systems. If you have a system of equations and you have some inclusion, maybe precisely some of the coefficients in front of some of the derivatives are of order epsilon squared, and maybe some of them are of order 1. And this was the idea of Valery Smyshev, and they called this a partial degeneracy. So let's have a look at an example. So let's take isotropic elasticity. Right? Remember that in each material phase, I wrote these down, and I think Kirill wrote these down too. But the difference between mine and Kirill's before was a factor of 2, because I was working with a symmetric gradient, but now we're just working with a full gradient. We have lambda I plus mu, 2 mu, no, mu I now. What happened? For some numbers, lambda I and mu I, right? Constants. These constants have to have a special relation to satisfy these conditions, but this is immaterial in my discussion. And now let's think of the following example. So this was If you're interested, you can look at my work from back in 2009, where you have, say, lambda 1 and mu 1 are order 1, right? So they are just some constants inside this region here, Q1, and this is Q0. Okay? But then inside the inclusions you have lambda 2 is order 1, but mu 2 equals order epsilon squared. Okay? So the high contrast would say that lambda 2 was order epsilon squared, and mu 2 was order epsilon squared. But the idea of combining this spatial non-locality with temporal non-locality, and if you think of this tensor matrix here, you think, well, I want some derivatives to be soft and some derivatives to not be not so soft. And here you have a particular example. So what does it mean? Well, these things have very physical meaning. And it means that your inclusions asymptotically are hard to compress. That's what the lambda coefficient refers to in elasticity. But the mu coefficient tells you about shear. And this says that it's really easy to shear. So you imagine you have some kind of inclusion that's some kind of jelly. You can easily push a jelly and it will move, but try to compress a jelly. You'll have a bit more of a hard time. And that's what these kind of assumptions imply. But we've done a little bit of work, right, on the wave equation, especially in isotropic elasticity. If you did your homework in the first lecture, and this is interestingly, if you think, continuing this example up here, we had these pressure waves, right, and the pressure waves were divergences of the deformation, and the wavelength of this pressure wave was precisely lambda plus 2 mu over rho 0. And then we had the compression. These are called compression waves, and these are shear waves. What do I want to call it? I called this W, didn't I? And they were the curls of the deformation. And we showed that the wavelength of W, there's some factor 2 pi that I'm probably missing. There's always a factor 2 pi somewhere. Not what I wanted to focus on. But mu and rho, right? So if you remember, if we had an isotropic material, homogeneous material with lambda coefficients lambda and mu and density rho, the wavelengths were given by these two equations. Now let's have a look at what's happening here. So we have inside the matrix both waves are of order 1, like before. But now inside the inclusion, the compression wave P is of order 1, the wavelength. But the shear wave now as of order epsilon wavelength. So now you only have, for certain waves, you should expect that you will only have non-trivial behavior for certain waves, precisely the shear waves, and not the compression waves. And you should expect, from this intuitive idea of the work of Kirill, Valerian, and Vasily Zhikov, and then the leap in the idea of Valerian to partial degeneracies, you should expect this gives some kind of spatial as well as temporal non-locality. Okay? So now let's just play with the equations a little bit. So we want to talk about partial degeneracy. So let me formulate a partial degeneracy. So partial degeneracies now, I can go here, right? You guys can just write for partial degeneracy. Partial degeneracy. So we have C. This is our tensor. And it has a very special structure. It is precisely C1 ijkl, possibly function of y, plus C2 ijkl, a function of y. And we assume only this, that C1 is this big enough, Yulia? Yeah. So, in the high contrast, we assume that this guy was positive on the stiff phase, Q1, right? But now, with all of these ideas in mind, this mathematically formulates itself as assuming that C1 is nothing more than just non-negative, and Y can be anywhere in the cell. But then, of course, we need to guarantee some kind of solvability. And this is at least, we can keep on generalizing this until the cows come home, but there's no point. All I'm interested in is the idea, and this is sufficient. And M is symmetric. All symmetric matrices M. Okay? So this guy can be non-negative, maybe positive. Like in the high contrast case, it was positive here, 0 here. In the classical case, it was positive everywhere. In the homogeneous case, we studied on lecture 2. And now and in this case, you can see it would be positive on the matrix, but non-negative on the inclusion, because precisely the analog of these shear waves will be such that this tensor is 0. So when you take cross products of two vectors, you will get 0 here. And then this condition just makes sure that everything we're doing is okay. So if we put it in the precise mathematical framework, you would be able to guarantee solutions to equations in certain spaces. So, and this is the general assumption we're going to assume, right? And then let's look at these equations that we wrote. Well, if we remember that this equation was analogous to saying that our function, the gradient of our function, was 0 in the matrix. So the function was a constant plus some function on the inclusion. But actually what we showed is that u0, remember in our ansatz, for fixed x and t, say, was in a certain space. And we said this space was space of, say, I will just write c infinity 0 functions here. Just for people who are unfamiliar with Sobolev spaces. And the condition is precisely that c1 grad y of v is 0. Now, we proved this condition. But what we showed in the high contrast was c1 was actually positive on the matrix, which meant that the gradient was 0 on the matrix, which meant that the function was a constant on the matrix and arbitrarily defined in the inclusion. Now, if we go back to this example, just because I'm just throwing constructions at you here. So these are all order 1, and we remember that mu2 was order epsilon squared. Well, this space V then, there is a picture. So because the Ramey coefficients are constants, both positive in the matrix and order 1, it means here that the vector field must be constant, just like before. So here u is constant as a function of x. But inside the inclusions now, this constraint asymptotically disappears, and what it means is you're only left with the second Ramey coefficient. And if you look carefully, this condition precisely means that the divergence of u equals 0. And this matches up to what I was saying about imagining that this was some kind of jelly, because this condition precisely tells you that your function as a function of y is incompressible. So microscopically your field is incompressible. And this is captured by this space here. Well, this is the characterization of this space for this example. And it's also okay. And then we move on to the second equation, right? And we remember that actually the second equation, we could just write this. But here now, there is something very interesting happening here. The first instance of why you should expect non-trivial things to happen. And this is equal to 0. Now, remember, in the high contrast case or in the classical case, this guy was positive on its support. So this function was independent of y. And because this function was independent of y, u1 had a very trivial relation with respect to x in terms of the derivative of this function. But now, from this partial degenerate setting, we cannot guarantee this at all. If we think about this general setting here, this function will still depend on y. So, how do you handle that? And we're going to think, and we're just going to, for the sake of the rest of this discussion, we're going to consider the following case. So let's draw a picture. We don't need to consider this, and if you're interested, you can look at more work of my colleagues and I. We've been doing this in several directions, but let's put ourselves inside the framework that Valery Smyshlyav introduced in 2009 in his article in Mechanics and Materials. So maybe we're just inclusion this way, or you can imagine inclusions going in all three directions if you like, but it makes the picture ugly. Okay, I'll say it in words and draw it in one direction. So now we're going to imagine that this is Q1, right? And we're going to imagine that this is Q0. And this is Q1, and this is Q0. So this is disjoint inclusions. And these are fiber inclusions. So the important thing is the inclusion Q0 intersects the boundary of the periodic cell. And this can happen in all three directions. I just draw it in the picture in this direction. In one of the three directions. And let's pick a special form of C1, right? I'm going to say, so chi1 is the characteristic function of Q1. And chi0 is the characteristic function of the inclusion Q0. And let's assume that C ijkl of 1 as a function of y equals chi1 of y. What shall I call this guy? Let's go with A now. A1 ijkl y plus chi0 y A2 ijkl. Okay? So A1 is only defined on Q1, A2 is only defined on Q2, and I'm going to assume that A1 is positive and A2 is negative. So A1 is positive on its support and A2 is non-negative on its support. This is a particular class. A subset of this class is precisely what Valery was formally studying in his 2009 paper. And when I mean positive and non-negative here, I mean non-negative coincides with this. Positivity means there is a constant, so you can bound it from below. And then we look at our space V, right? Let's have a look at our. Let's have a look at our space V. So now I see C1 as this structure. So it precisely means inside Q1, because A1 is positive, the gradient is 0. So again, the function is a constant. But inside Q0 now, there is this constraint that appears. So it's not like, so classical is the function is constant everywhere. High contrast means the function is constant in the matrix and arbitrary in the inclusion. And this is somewhere in between, where it's a constant in the matrix and constrained by this fact in the inclusion. Think of this example. So it's a constant in the matrix, but it must be incompressible, satisfy the divergence-free condition in the inclusion. So we can say that our function u0 of x dot t is in V, so in a certain with certain regularity. We have u0 of x y t equals u of x plus v of x y t. Okay, and V is in a space, I'll call it H, which is a subset of the periodic functions. H1, I like to write H1, but okay, I'll put C infinity for you guys again. So it's a subset of the periodic functions, such that A2 grad y V equals 0 in the inclusion. So if I'm in this case, then the V is supported only on the inclusion. But the reason I have to put periodicity here is it's not quite precise, right? periodicity in 0, where I mean on the boundaries that don't intersect the boundary of the cell, the function is 0, but on the boundaries that do intersect the boundary of the cell, the function has to be constant. And now I look at my equation B. So let me rewrite it again. So again, it solves the exact same. The reason I wrote the equations for the high contrast in such generality is because I was thinking of this next. So it solves the exact same equations. So again, divergence of y of u1, of c1 grad y of u1 plus grad x of u0. Remember now that these guys are a function of x, y, and t, both of them. This is a function of y. The equation I just rubbed out and put here is the exact same equation. This is the weak formulation of the equation. Okay? And now, remember, we had this more interesting equation here. Again, it's the same equation, and we had to assume for solvability that the right-hand side, which is all of these terms pushed over here, had to be orthogonal to any function in this space V. So we can write this condition again. So what does it look like? It was divergence of x. So I'll write it in index form. So the integral over Q now of C1 was this term plus right. So I promised that I would only use half an hour of the allotted. Oh, see, almost ran out of time. A shame. Okay, so I can't say much more now because I don't want to make the rest of the afternoon late. But what I will say is, so now the equations of the same structure, of course, on an abstract level. But then we have to start considering in particular examples what these equations look like. Remember, in the high contrast case, this space was precisely just functions constants on the matrix and arbitrary on the inclusion. So you pick functions constants on the matrix here, and then you pick functions arbitrary on the inclusion, and we got these equations. But there are two new terms here. If I just quickly finish, so if I think about this example here, there are two new terms, right? Well, my U1, again, my U0 has a special structure. It's a function U of x plus a function supported on the inclusion. So my U1 has a special structure. It's precisely the same cell function that's appeared before. Plus some function I'm going to call W1. Okay? So then when I put this representation into this equation, we'll just speak now, I won't write any more equations. When I plug this representation in here, we will get the term that we got before that gave us the homogenized matrix plus some new term. And this new term, we hope in examples will account for the spatial non-locality. And it's precisely given by this this term here and this term here. So let's just say, okay, I can go here, right? So the idea is, now we have this mathematical framework, let's try and think of some physical examples in applications where we get this spatial non-locality. And I want to look at this term. So this will be the new term. If it gives us any, if it's non-zero, it will give us something new in the equations, and hopefully it will give some kind of spatial and temporal non-locality. And there is not on some level it's unsatisfactory because it's a mathematical example and not an example from applications. But in Valeri's 2009 paper, he actually shows that you can pick your tensor A2 in such a way that this term will be non-zero, and it will precisely give the spatial non-locality. So frequencies and wave numbers in the direction of the fiber where waves cannot propagate. But let's just think of so some work that I've done on this. So maybe I can show you the proofs afterwards. But let's say, imagine we have disjoint inclusions. 1, right? Lowercase 1. And A. Suppose the inclusion was stiff. I'll call this object some I of phi. It's a functional that depends on phi. And suppose your inclusion is stiff. So what I've done now is I've just flipped it. So here the coefficients are epsilon squared. And here the coefficients are 1. This is some kind of consistency test. Then I of phi equals 0 for all phi. And even more. And in fact this guy is 0. If I look at this guy. So I call this J. So in fact in this problem, if you flip the coefficients and make the inclusion, isolated inclusion stiff and the matrix soft, then you don't even have a 2-scale homogenization problem. You just have a problem purely on the variable y. So you lose your scale interaction effect and you lose your possible chance of spatial non-locality. So this is some kind of consistency for why we want the inclusions to be soft and not the matrix. And then B. Let's suppose we're in case 2. No, case 1 now. But high contrast, like this. And we have this. So we have partially degenerate inclusions, but our inclusions are disjoint inclusions. And remember the formal motivation of the ideas in Kirill and Valeri and Vasily's paper, and then Valeri's leap from this in his 2009 paper would basically tell you we must have fibers. So let's study disjoint inclusions. Well then, again, this is a work of mine from my 2009 master thesis. You can see that I of phi is 0 for all phi. And actually, there is another term here, which I can write, which looks like a new term as well, which is of the form grad ux. What is it? It's of the form. Yes, it is of the form grad y uy xt. What do I want to say here? I don't think I need to. No, I don't need to say anything else. That's it. Again, this functional is 0. So this functional is the only new functional that can give us spatial non-locality. And it's identically 0 here. So we start building up some kind of recipe. If we want to construct some kind of composite that has temporal and spatial non-locality, the inclusions have to be soft. And the inclusions have to be not isolated. They have to, at least in one or more directions, extend. So they have to be like a fiber-like structure. And I don't want to take any more time with the next speakers, so I will finish here. And this was the crash course that, to get you up to this point. And of course, if you're interested in this, then please go read some of the articles of my colleagues and I, and we will be very happy to discuss these things with you. Thank you. So I always say thank you before questions. I presume there's no questions. I didn't mean to. Were there any questions? Well, actually, maybe because of the time, you can ask me questions if you have any afterwards.